Welcome to today's AM Academy webinar, part of our ongoing series that's designed to make cutting-edge materials science and engineering knowledge more accessible. My name is Zara and I'll be your host for this session. And today's talk is on silver nanoparticles at scale, precision engineering for sensors and conductive materials. I'm very pleased to introduce Dr. Mikhail Kovalev, who's the Director of Product Development at Accelerated Materials. And in this session, Mikhail will explore a comprehensive overview of silver nanoparticles and the applications, the performance and quality requirements, using a flow chemistry approach for silver nanoparticle synthesis and its comparison to batch, and synthesis using the K1 reactor for sensors and conductive pastes, and a techno-economic analysis of scalable silver nanoparticle production. We'll also leave some time at the end for Q&A, so feel free to drop your questions into the Q&A box throughout the session. And with that, I'll hand over to Mikhail to begin.
Yeah, hello everyone. Thank you for joining today for the session about the silver nanoparticle synthesis experience in accelerated materials. So I will share the slide deck to begin with. Today we will be talking about the silver nanoparticles and how to engineer it precise, and we will review some applications on it. So here is the small outlook for today's session. So I will review a little bit on the noble metals nanoparticles. Also, we will discuss why silver is unique in the role of those metals, and what are the nanoparticles industrial applications, and the flow chemistry approach for the nanoparticle synthesis and its comparison to the batch systems. And of course, the synthesis of the silver nanoparticles using K1 reactor is our experience. And at the end of the session, I will touch a little bit on the techno-economic overview for the production of silver nanoparticles and the current market outlook. So to begin with, let's start with the noble metals. What are they? I believe most of you are very well known that the group of noble metals, for example, silver, gold, and platinum, are quite rare in the crust, in the Earth's crust, right? So that's why their price are quite high. But with it, they have a lot of very nice properties like corrosion and oxidative resistance. So makes them really chemically inert. So under ambient conditions, and also they usually exhibit high electrical and thermal conductivity. So which also makes them quite unique in comparison to most of the other metals. So noble metal nanoparticles, they exhibit even more additional properties, right? Besides the chemical resistance, they also can exhibit some catalytic activities, and for some of them, they can have different optical properties in their absorption bands, so that you can tune for the visible and IR or ultraviolet lights wavelengths, right? So of course, if you look at the applications, right, it's having like a lot, for example, for the conductive things, sensors. They also can be used as a catalysts, and due to their inertness to the human bodies and human cells, right? So they can be used. They can also be applied as antimicrobial additives. So yeah, and what makes actually silver unique? And what are the current what are the properties of those in the comparison with other metals? So, for example, if you look in the row, the copper, silver, and gold, so you can see that the color are different. So the copper is red, silver is gray metallic, and the gold is yellow. They have quite similar resistivity. So this is the micro-ohm centimeters. So where the silver has the lowest one, which is nice for the conductive applications or for wires, right? Thermal conductivity are also very high for those metals, especially again for the silver. And yeah, it also could be used in some thermal conductive pastes, right? Also, you can see the oxidative, so potential volts against for the standard hydrogen electrode, where this copper is the easiest to oxidize. Silver still can be oxidized, but it's the potential is higher, and the highest potential is for the gold, right? All of those metals exhibit a very good antimicrobial activity in their nanoform, while in the bulk form they are quite inert. And of course, because of the oxidation, so those metals can dissolve, especially in the nanoform. So that's why is the toxicity for copper going to be higher than for silver and for the gold. While the gold is very difficult to oxidize and dissolve to form an ions, right? So that's why it's it's going to be quite inert. And of course, if you look at the natural abundance, copper is pretty abundant, while silver and especially gold are very rare. So, and of course, this one affects a lot on the price. So where the gold is 10 times more expensive than silver, and the silver almost 100 times more expensive than copper. All right, let's go for the some areas of application for the silver nanoparticles, right? So since that the bulk silver and the nanoparticles exhibit very good thermal and electrical conductivity, so that could be widely used as a conductive pastes and inks. And because of the nanoparticles having some the so-called the surface plasmon resonance, and that's why they could be used as an optical sensors in the biological and general use, and also as an antimicrobial additives. Of course, these nanoparticles can be coated or decorated for different semiconductor types like titania or zinc oxide. So that can also make some self-cleaning coatings. Because of it, it will be able to generate some active oxygen radicals under the sunlight irradiation or the light irradiation. All right, so let's go for the let's review some exact the applications, and what are going to be requirements for the nanoparticles or microparticles, right? So one of the most common use for the silver particles are electronics, so as a conductive paste. So that are used for mostly used for the printing of PCBs, RFIDs, flexible circuit, right? And one of the most common methods of application is screen printing. So usually the requirements for this should be as low as possible the resistivity of it. The paste should has like relatively high viscosity, something like from 6,000 to 11,000 centipoise, right? And of course, the matrix should have like excellent adhesion to the various substrates, and to get the as low as possible resistivity. So we probably want to have a high solid content, right? The other application of the silver nanoparticles is silver inks, right? Where it's also can be used for PCB, RFID, and flexible circuit printing. However, the method of application is generally inkjet printing. So for that one, the requirements also still pretty much the same as for the pastes. However, the viscosity should be very low, like 10 to 20 centipoise, because of the inject nozzle is very small. So that's you need to squeeze the ink through the nozzle of the diameter like 10 micron, 10, 20 microns. So to generate micro droplets. So that's why the viscosity of the ink should be very low. There are a lot of requirements. Let's review the requirements for the nanoparticles for the both applications. So for example, in order to achieve the good viscosity and the good flow characteristics for the pastes, right? So that nanoparticles probably should be submicron to micron size, right? And also that should be close to spherical shape in order to have like a nice fluidity and yeah, have a better variation in the viscosity adjustment. While for the inject printing for the inks, right? So the size should be very small in order to have a low viscosity dispersion of the nanoparticles inside the inks. And of course, you cannot have like the micron size particles for the inkjet printing because the diameter of nozzles usually is like 10 probably, and or 20 micrometers. So that's why is the size of the nanoparticles and the size distribution here are very important. And of course, we should also need to mention here that the silver has a high density, so that the specific gravity. So that's why it's like if you have quite large particles, so they will precipitate in most of the common solvents because of the usually, for example, the water-based inks, right, where the density of water is 1 and silver is 7, so it will be precipitate quite quickly. So that's why also the small particle size is important to make a stable dispersion. All right, so let's go for some electrochemical sensors. So it's also part of the electronics. So where the particles are used to in the application of small molecule detection, also environmental pollutant analysis. And here is the requirements are not so strict as for the silver inks. So the size can vary for different matrices, and also it could be various morphologies in order to have different catalytic effects that can be helpful in the analysis of the molecules. And it's also need to be able to be deposited on some conductive substrates where the readings are performed. And the next is a general one. Maybe everyone probably remember from the COVID times that it's also for the small molecule, could be used for the small molecule detection and also for the antigens detections, right? And here is the one of the MIT startup that use a different size silver nanoparticles as the color that having a different surface plasmon resonance. And in order for the particles to exhibit the surface plasmon resonance and to be able to absorb light at the different wavelengths, so the size should be from 5 to 50 nanometers, and it could have also different morphologies. And of course, one of the most known application is the antimicrobial. So where you can see that we can use it as an additive of the silver nanoparticles for making surfaces antimicrobial, and it's also sometimes used as a wound healing agent. Yes, of course, the requirement here is that the nanoparticles should have a broad spectrum of the antimicrobial activity. It could be different morphologies and probably as low toxicity as possible to human. And self-cleaning coatings is also one of the interesting applications. So over here you can see that the silver nanoparticles are decorated on the zinc oxide on the SEM picture on the left, right? And it also can be used as an additive to different paints or coatings that can help, yeah, to generate the active oxygen species under the sunlight, so that can oxidize some pollutant. And of course, the general requirement is that it should has as less color as possible in order to be able to make some decorative coatings and so on. All right. So let's go a little bit to the practical and theoretical part. So we can start. I will review a little bit on the method of the synthesis and scale up of the silver nanoparticles. So traditionally, silver nanoparticles were synthesized in batch or micromillifluidic these days, right? So usually the batch we assume that it is some flask or probably some bucket or maybe some tank where you can synthesize the particles. So practically for batch is very easy to set up. So you can take any flask or the reactor, right, or tank where you can do the reaction. Yeah, and usually, for example, flasks are very cheap to use in the lab for your optimizations. But the biggest problems with that is usually the scaling up is difficult, and batch-to-batch reproducibility also sometimes is not very nice. The other approach is micro millifluidic devices, right? So you can control very well mixing conditions, right? So that's why you can have a high rate of reproducibility in the future. However, these reactors usually possessing a lot of problems that you need to dilute a lot of your reactants in order to prevent clogging. They are also not very cheap, and the scaling up is possible, but you need to put a lot of micro millifluidic chips in parallel in order to get some substantial amount. And of course, it's going to be even more expensive than for the lab use. Yeah, in our case, we have used for the silver synthesis our annular flow reactor, where you can see that it possesses tube and tube and tube reactor, and it's actually benefits a lot from the very high controllable mixing conditions, right? So you can control very precisely. So that's why the reproducibility is would be very good compared to the batch systems, and also it have a very low fouling, so that's why you can use higher concentrations, and of course the space-time yield is going to be way higher compared to the micro and millifluidic devices. And yeah, the controllable micro mixing conditions get you to the high reproducibility. And let's compare the annular flow and the traditional batch systems. So while in the case of the flow reactors, you need to have a good manifold that can split the flow equally, and you can achieve the scale up by just numbering up of the reactors, right? And in this case, you need to optimize the reaction conditions or process once for one reactor, and after that, the scale up becoming quite easy task. It's much more difficult for the traditional setup. So if you look at the left, you can see that you, for example, prepare or made your synthesis and it worked perfectly in some flask 5-10 centimeters, right, in height. And then you need to scale up to maybe like tens or hundreds kilograms a day. Then you need to scale in proportionally the vessel where the reaction is performed. So, and with the scaling of the vessel, all the parameters like mixing, mass transfer, and the heat transfer are going to change dramatically. So that's why the reaction in a small flask and in a big vessel are completely different tasks, and you need to do additional R&D in order to optimize for the big vessel, in order to optimize the conditions of the synthesis for the big vessel. And this actually makes a lot of complexity and then a lot of investments for, especially when you are working with the noble metals that are very expensive. And that's why it's like many people these days trying to go for the flow synthesis, where the scale up is more direct and linear compared to the traditional batch systems. All right, so let's go to the practical part, where we also discuss on the synthesis in the annular flow reactors. And the practical approach are pretty much similar to the batch one. So where you have some silver ions, you're mixing with the reducing agents, where they form some seeds. And after forming the seeds, it's going to grow into the nano and microparticles. So usually the source of the reagent source are quite classical, which is also used in most of the batch systems, right? So the silver ions is very known source is the silver nitrate, where it is soluble in most solvents, and yeah, most common like water or ethylene glycol, and yeah, well-known reducing agents like sodium borohydride, hydrazine, or ascorbic acid, right? And of course, in order to prevent overgrowth of your particles and stabilize the dispersions, various capping agents and surfactants need to be used, right? And how the synthesis has performed in our case. So usually we use the K1 reactor that's schematically shown here. And we have two reagents, and basically one reagent is the silver nitrate, and the reducing agent would be sodium borohydride, hydrazine, or ascorbic acid, right? And for the nucleation and growth control, we use the different capping agent like citric acid or polyvinyl pyrrolidone. And to control the mixing conditions, we varied the reagent and the gas flow. As you remember, there was the reactor consists of the coaxial 3 tubes, coaxially located. And yeah, let's go to the practical part. What actually the results? And here is some example for the silver nanoparticle synthesis, where you can apply different shear force in order to control the particle size and the particle size distribution. And here the reaction has been completed without capping agent and with relatively high silver nitrate concentration, about like 0.5 mole per liter, right? Which is very difficult to do in the microfluidic devices. So, and you can see at the low shear force, we can get a wider distribution, but however, the smaller nanoparticles. In the middle range, where we can get a little bit bigger nanoparticles and still a bit bigger the particle size distribution. And if you have a high shear rate, so that can probably promote better the crystallization, and you can get 3 to 6 micrometer particles. And this is again without adding any of the capping agent, so you still can do the control of the particle size. So here is some of the synthesis in the annular flow reactor, but the citric acid as a capping agent, and the reducing agent was the hydrazine. So you can see that at the small concentration of the citric acid, we have a mix of the particles. So some of them are very large, almost 6 micrometers, with a lot of the nanoparticle fraction. Usually it is like a submicron, around like 300, 400 nanometers. And if you have like a medium concentration of the citric acid, so you can get a good fraction of the 300, 500 nanometer particles. And the high concentration of the capping agent, the particles are very small, about 15 to 30 nanometers. And you can see that with this range, you can cover most of the requirements for the conductive pastes, right? And for the conductive inks formulations. And we have also found very interesting phenomena, right? So you can see that we can prepare the particles around 300, 400 nanometers. Maybe here is a little bit smaller, even 200 nanometers. And if you do annealing at the 120, so all the particles are intercalate. You can see on the right side. So the particles are quite well connected. So meaning that if you formulate the paste or conductive paste with those particles, they will have a very good fluidity and very nice. You can add quite substantial amount of the silver nanoparticles in the formulation, and after deposition and annealing at 120, they will intercalate well. So assumably it will improve a lot of the conductivity of those pastes. All right, so this one is the latest and more detailed overview for the inks. You can see that at the higher concentration you can get from the SEM images, we can see that the particle size is like 15, 30 nanometers, while the on the right side there is a DLS size distribution, and it's about like from 6 to 15 nanometers. Actually, the D90 is 14 plus minus 2.5 nanometers. So it's a quite narrow distribution, I would say. And we will observe that this dispersion was very stable and can be stored for quite a long time on the shelf without the precipitation of the particles. So to summarize it, yeah, so we have been prepared a different silver micro and nanoparticles. So, and all of those particles has the shape close to the spherical for the best viscosity and flow characteristics. And also it has shown a very nice intercalation after annealing at 120 degrees Celsius. All right, let's go next. And here is the some of the our experience for the silver colloids for optical sensing preparation and the synthesis. And I will do also compare here a bit with the traditional batch mixing. So a little bit of a theory, how it's prepared. So basically, in order to prepare the silver colloids with which that are exhibiting the surface plasmon resonance, so the particle size distribution should be quite narrow, and the particle size should be relatively low, from like 10 to 30 nanometers. So over here, usually the process is pretty much similar to the batch one. So where we have used the silver ions and reducing agent to generate the seeds. So after that, we mixed seeds with silver ions and then mixed in our reactor with the reducing agent and the stabilizer. So we got the caped nanoparticles. And you can see that in the theory, right, the surface plasmon resonance is where the particles oscillates in the electrical field that the light possess, right? And it can have the particles inside the colloids could have a different absorption range. So over here you can see the example that one color is like yellow, another one is the green. So two different particles has the different absorption. So let's go by the steps. So first we have generated some seeds, and at this time there was like silver nitrate with sodium borohydrate, and the polyvinyl pyrrolidone was as a stabilizing agent. So you can see the DLS graph on the left that resulted the particle size about 9.2 plus minus 2.1 nanometers. And it's actually having like the characteristic absorption more than at about 350 nanometers, indicating that the particle size is very small. So the next step was mixing with the growing of the particles, right? So again, we have used as a reducing agents the sodium borohydride and ascorbic acid. So it's just to compare the highly active reducing agent and like the reducing agent with the slower kinetics, slower reducing kinetics like ascorbic acid. So, and also for the same concentrations, we have done comparison on the batch where we mixed in the flask and the annular flow reactor. So you can see here that the reducing agent is the sodium borohydride. So you can see that we can get different colors of the solutions, right? So where the 1, 2, 3 are the K1 system with annular flow, and for the flow reactor, and the samples with A is a batch system. And there are some also, yeah, the result was quite interesting that the flow reactor and batch system can produce very different results even at the same concentrations. And in general, K1 and or annular flow shown a narrow particle size distribution. And you can see that some SEM pictures that shown some additional superstructure building upon the sample drying and on the SEM part, right? That's just an interesting fact. So for the ascorbic acid, you can see it's is a little bit different behavior. So we can also get some very narrow distribution for the annular flow reactor. But however, for the samples B and C, uh, where the concentration of silver ions and was larger, so we get a larger nanoparticles that are already not exhibiting the surface plasmon resonance, and I'm referring to the samples 5 and 6. And there are some SEM pictures on the bottom. All right. So there was also some experiments with the decorations of the silver nanoparticles on the zinc oxide. So zinc oxide can be converted into the zinc peroxide. So after that, if it is mixed with the silver nitrate, it can be reduced back to zinc oxide, and the nanoparticles will be decorated directly on the particles, right? And over here you can see that it's exhibiting a very good antimicrobial activity. So it's indicated by the circles around the clear circles for the E. coli and the Staphylococcus aureus. And the active amount is very small. Is also can be below 100 ppm. To while you add into the different matrices. And at the end of my presentation, I would like to review a little bit of a techno-economic analysis. So here is from the open sources what are the silver nanoparticle market, and you can see on the right. So almost more than 34% of all mined silver is used as in the electronics applications. So besides like different traditional one like jewelry and the investment, and it looked like that the calculated annual growth rate is about 7%. So meaning that by 2030, the global conductive silver paste market can reach around 12 billions. And of course, the main drivers for those applications are photovoltaics, PCB printing, and flexible circuits, sensors, and a little bit of the other applications for the conductive silver paste. All right, so here is some review of the nanoparticle production with the annular flow series, where we do have like K1 means that the 1 kilogram a day, K10 is 10 kilograms a day, and K100 system is the 100 kilograms a day, right? So the calculated production cost is about twice or maybe 1.8, 1.7 times less compared to the batch systems, for example, like 50-liter reactor, 100, 1,000 and 10,000 liter reactor that are capable to produce similar quantities. And of course, the OPEX operating expenses are also low. And if you look at the investment and the investment reduction and the OPEX reduction for the K systems, you can see the significant decrease compared to the batch systems. And of course, everyone before investing would like to know how fast you can reach the break even, right? And over here, for example, for K1 reactor, of course, that the production cost is quite high, so probably the break even is never achieved. However, for the K10 and K100, you can achieve it quite quickly. And at the K10 scale, for 10 kilograms a scale, it's already possible to generate profit, unlike for the batch reactor, where the product cost is still more than the average on the market, 4.5 thousand per kg of particles. All right, thank you very much for the for attending it. So I'm looking forward for questions.
Yeah, thank you so much, Mikhail, for that insightful session. We had a few questions come in, so let's make our way through those. So the first question is, what solvents are used in order to dissolve silver nitrate and reducing agents?
So in our case, we have been using water. So most of the silver nitrate is very well soluble in water, and as well as all those reducing agents. However, it also can be used different, like ethylene glycol or the other alcohols.
Great.
Thank you.
And how can someone buy the K1, and how does AM work with customers?
Yeah, K1 is possible to, so we have some the contact details in the emails, so you can contact us anytime, so we can provide all the additional information how to buy it, right? And also we usually work with the clients, so we have included support. We also do have in a package some machine learning framework in order to plan your experiments very well. So we will be happy to discuss about it. Thank you for the question.
Perfect. And what are the production rates for K1 and K100?
Yes, the production rates, as I have mentioned, so K1 usually is 1 kilogram a day, and K100 means the 100 kilogram a day. So because of this is a flow system, so it can be operate 24/7. Just stop for the maintenance or some cleaning from sometimes. But of course, it's also this rate is dependent also on your product density. So I assume that the silver having like a high density, so probably the yield per day could be much higher than 1 kilogram a day. So maybe 3-4 times higher. So probably you can expect if you run it 24 hours, you can get 3-4 kilograms for K1 and maybe 200-300 kilograms for K100.
Great. And how is shear rates controlled?
Yeah, thanks for the question. It's actually a very good theoretical one. So I can probably reiterate it with sharing the slide again. Just give me a moment. On the animation here. I hope you can see the animation. So we have actually a reactor that consists of the coaxial tubes. So you can see tube 1, tube 2, and tube 3. So where, for example, for the outer tube and for the middle tube, you supply reagent 1 and reagent 2. And in the middle, you pump the air with very high velocity. So that can help to mix the reagents inside the tube. So meaning that you can control the shear rate by the rates of the two reagents and the airflow rate. Yeah, thanks. Hopefully it has answered your question.
And we have one more question. What flow parameters impacts morphology?
Yes, this is a very interesting question. Thank you. There are a lot of different flow parameters. So as we already discussed, the two flow rates of the reagents, and also the airflow rate. And of course, the different morphologies can also be dependent on the reagent concentrations. So generally, it's not a lot of parameters to control, but generally it is the reagent concentrations, liquid flow concentrations, and the airflow airflow rate. Yeah.
We've had one more question. How is the K1 system controlled?
Yes, K1 system usually can be controlled if you look at the schematics. So this is the schematics representation of the K1 system. So you have seen that in the middle capillary, the compressed dry air is applied to control the mixing conditions, while two liquid flows goes into the outer and into the middle tube, right? Is controlled by the low pulsation liquid pumps. Yeah. Thank you.
Great, thank you. Thanks for answering those questions, Mikhail, and thanks again for that really insightful session. And thank you to everyone who joined us today. A quick reminder that this webinar is part of our ongoing AM Academy series, where we share knowledge and tools to help accelerate materials innovation. You can explore more webinars, articles, and technical resources at acceleratedmaterials.co/AM Academy. And we will be sharing this recording on our YouTube channel shortly. So if you want to revisit any parts or share it with your colleagues, do keep an eye out. And thank you again for spending your time with us. We really appreciate it. Have a great day, and we hope to see you at the next AM Academy session.
Thank you.